Here, we will discuss the main ideas of StyleGAN3 architecture. I will begin by introducing an intuitive understanding of the StyleGAN architecture, and Benedikt will cover the details of the code implementation. This discussion is a part of our survey paper, Deep Learning for Face Generation and Editing. To learn more, check the links in the description and visit our GitHub repository. StyleGAN3 is an improvement over previous versions of this architecture. The architecture itself has different use cases. For example, it can generate in high resolution faces which do not exist. Or, for example, here, the same architecture, but trained on a different dataset, can generate shoe which doesn't exist. Another important use case is that this architecture allows to merge two objects such that the resulting object contains features of both sources of information. If we merge source A and source B, the resulting image will contain information from both source A and B. This architecture can also be used to edit faces. For example, change hairdo, gender, age, smile. One problem is that this editing technique works well for a static image. For example, it can be a photo of a person, and we can change certain parameter of this face. However, if we want to use StyleGAN2 architecture for some dynamic things where an object is moving, some artifacts become visible. These artifacts are visible on the left side on the videos created with StyleGAN2 architecture, namely the texture sticking problem. You can see an unnatural visual flow where texture like hair or wrinkles would appear stuck to the screen and do not move naturally with the face. On the right side, you see videos created with StyleGAN3 architecture, where this problem doesn't exist. So in this work, some improvements were conducted for alias-free generative adversarial networks. One of the main problems was that the synthesis process of typical generative adversarial network depends on absolute pixel coordinates in an unhealthy manner. Thus, some image details are glued to image coordinates instead of object. The improvements resulted in internal representations which are fully equivariant to translation and rotation, which is a great improvement for generative models for video and animation. Here you can see an example of transition equivariance. We have a generator with a number of layers that can generate an output image. If we take activations of one layer in this generator and shift pixel activations for all channels, left or right, the output image should also demonstrate similar displacement. The input to the generator that generates an image is a 3D matrix with a number of channels and some spatial resolution. In StyleGAN2, the spatial resolution was 4x4, and in StyleGAN3, this is a 36x36x1024 channels matrix that is used as one of the sources of a generator. And this generator signal is later modulated by a style vector. One of the main ideas is that if we take this 3D matrix, this one or this one, and if we translate that up, down, left, or right, or if you want to rotate this matrix, the output image should also be translated or rotated without any distortion. This can be achieved with these improvement techniques. This figure enumerates improvements in StyleGAN3 architecture in comparison to StyleGAN2 architecture. For example, configuration B is StyleGAN2 architecture plus Fourier features. Configuration C is StyleGAN3 architecture plus Fourier features plus no noise inputs, and so on. Columns demonstrate metrics to measure performance of different configurations. For example, free share inception distance, the lower the better. Equivariance translation and rotation. Measured in decibel, the higher the better. In Appendix Section E, this equivariance matrix is described in detail. Basically, we take average pixel-wise mean square error between two images, and then this mean square error becomes denominator. In the extreme case, when two images are the same, this peak signal-to-noise ratio goes to infinity. So what are these configurations? For example, configuration C with only Fourier features and no noise inputs is almost as good as the final StyleGAN3 architecture. However, still not so good for equivariance translation and rotation. Only configurations T and R provide the final translation and rotation equivariance. Fourier features introduces changes to the first layer of the generator. In StyleGAN2 architecture, the first layer was a variable of size 4x4 x 512 channels, and that was a learnable variable, which means that the final values of this 3D matrix were defined by gradients while training. We can hypothesize that could lead to not very informative channels in the first layer. For example, imagine a situation when the left half of this not informative channel contains high value and right part contains a low value. Let's focus on one of the pixels. Then what happens if we translate this channel right? The value under this pixel coordinate will not change, which could lead to ambiguity in translation of the output image. But what if you make first layer channels represent waveform patterns, where each channel can represent a waveform of different parameters, like frequency, direction, or the middle point. Then we can randomly generate all channels of the first layer and make it not trainable. Such waveform patterns probably will allow a better grip and will have benefits for translation and rotation operations. For that, we will need a better spatial resolution of the first layer, for example, like 36x36 in StyleGAN3 architecture. These waveform patterns can be produced with Fourier features, which are randomly generated during the initialization of the model and become frozen during training of the architecture. These Fourier features result in two-dimensional waveform patterns in channels of the first layer. Next, configuration C proposes no noise inputs. Namely, here we don't have noise inputs anymore, as in previous iterations of StyleGAN architecture. Configuration D, simplified generator, implies less number of layers, for example 14 layers in StyleGAN3 versus 18 layers in StyleGAN2 architecture, as well as a reduction of some regularization techniques while training, for example mixing the W vector from different samples. Configuration E, boundaries and upsampling, introduced bigger padding areas with zeros, approximately 11 pixels from each side, and the upsampling procedure where we add zeros between activation values of the previous layer. In case of 2x upsampling, we have a single zero between two values, and in case of 4x upsampling, we have 3 zeros between each activation value. We also do cropping to preserve the size of the layer. This is necessary to prevent leaking of absolute coordinate information from boundaries into the network. Configuration F, filtered nonlinearities, introduced additional upsampling before an activation function and downsampling after the activation function, such that the size of the flow doesn't change. Configuration G, non-critical sampling, is related to a better cutoff frequency for filters while upsampling and downsampling operations. Configuration H, transformed Fourier features, introduced influence of W style vector on the first input layer of the generator. Namely, it's a fully connected layer from 512 dimensions to 4 dimensions, which represent translation and rotation values for the first layer. Configuration T, flexible layers, introduce a dependency between cutoff value of upsampling and downsampling filters and a sequential number of a layer, which are described in detail in the flexible layer specifications and also shown in the figure 4c. The rotation equivariance configuration R introduces 2 changes. First, 3 × 3 convolutions were replaced with 1 × 1 convolutions on all layers. As you can see here, for configuration R, 3 × 3 kernels were replaced by 1 × 1 kernels. Thus, in this configuration, only the upsampling and downsampling operations spread information between pixels. And second, sync-based downsampling filter was replaced by a radially symmetric jink-based filter. This was done for all layers except the 2 last layers. Also, during early training, the discriminator sees all images using Gaussian filter to avoid early collapse of the generator. Now let's take a look at this video demonstration. Here you can see 6 different configurations, namely B, E, F, G, T, and R. Here you can see equivariant translation loss measured in decibel, the higher the better. First column shows what happens with the output image if we translate the StyleGAN input. Second column demonstrates what happens if we translate input and then translate back the output image to the original coordinates. The last column demonstrates the overlap error between the original image and image from column 2. Similar demonstration is presented in video 6. These are 3 different configurations, T, T plus P4, and R. The metric demonstrates rotational equivariance for these configurations. In decibel, the higher the better. This video demonstrates rotation and translation of StyleGAN3, R above and T below configurations. First column demonstrates an activation of a single selected channel in a first layer of StyleGAN3 architecture. Second column most probably demonstrates activation of 3 selected channels in intermediate layers assigned to RGB channels of this visualization. And the last column shows the output image.
So the project also contains a visualizer that shows how the generation of the output images is done. So we have different parts. So the most basic one is just to load pre-trained models. So we have multiple sets of pre-trained models that classify first in StyleGAN3 and 2. So we can see the generated image before the changes and the generator after all the changes. For StyleGAN3 we also have the differences of 2 configurations. So the bottommost configurations, which were first which is the most translational equivariant. So the T1 here, and the R1 is the most rotation equivariant version. And the last part we can load here are the different datasets that are trained on. So we have the FFHQ ones. So for StyleGAN3, this is the loaded one, the normal FFHQ. We also have the AFFHQ, which are animal, and yeah, all the other ones. That's on this part. Then what was also mentioned is that we can style mix, so we can select the random style vector with this one. So this is base vector we are working on, and then we can mix with another one. For example, if I select the first three, then the first three layers of the generator are supplied with the other vector. So the more I add, the more it will transform into the second selected vector. What I can also do, one, we are just at the location of the style vector. If we go to 0, we get like an average image of the generator, so all values set to 0. And then we can go along this style vector and show some transformations. What we also do, what was shown in the videos, we can do just small variations to the original latent vector. So we can drag this and go along in different directions and do these smooth transformations. Then what the visualizer also provides is a detailed analysis of all the layers. So for any given generator, we can just show how each layer is represented internally. For the output, we have just 3 channels, which are the 3 output channels. We can view each channel independently, but we can also do this for all other layers. So in this layer, we see we have 431 layers, and then we can see each layer and how it behaves. So what was added on my side was the cancellation of or the scaling of different layers. So if we have a specific layer, let's go to the 10th layer, we can now scale specific channels from this layer. The first channel in the 10th layer, and this is the first channel after scaling. Now the scaling factor is 0. We can simply scale the output of the layer and then go on with this. What also can be done is to just scale a complete layer, so all channels of one layer, let's say to 0. And what we see here is that basically if we cancel out one layer, the output just gets a uniform color, which can be explained that there is no side channel in the model. So all informations except for the style vector are just passed from one layer to another. So if we cancel out one layer completely, we won't get a reasonable output. And then the last part, what is basically the main feature of this visualizer according to StyleGAN3, is the translation and rotation part. So what we can do is translate the input layer. So this is one channel of the input layer, and we can just translate it, so move it in any direction and rotate it. And what we then see is that the output image is equally translated without artifacts and also rotated without artifacts. This drastically changes if we don't use the R configuration. So example, if we use the T configuration of StyleGAN3, we see, okay, translation still works, but rotation doesn't work at all. So this is nicely shown in the visualizer. And we cannot show this for StyleGAN2 because StyleGAN2 didn't have the ability to translate and rotate the images. So if we select StyleGAN2 database, this one won't work. So what we see here is for the T model, that rotation won't work, but for the R model, rotation will work seamlessly. To better show this, it has an untransform option, so that the transformation that is passed to the input layer is inverse applied to the output image, so outside of the model. So if we apply the untransform, we can then rotate the image, also the input, and we see basically inside the image nothing won't change, but we get these corner sections because the original images or the output image is a rotated one. Same goes for translations. So what we basically see is, okay, it works. So no matter what transformations or rotations we do, the content of the image won't change, as opposed to the T configurations, where we see, okay, translations will work without problem, but rotations won't. So this drastically changes. We can also see how these rotations and translations affect the input. So if we select a single channel of the input layer, we can see that it is simply transformed. So for translation and for rotation, we can also do this untransform here, but it doesn't make much sense. And also we can see that some rotation and transformation information comes from the style vector. So if we change the style vector, we basically get the same channel output, but slightly transformed and rotated, and also smooth. Get the same for all other. So we have basically a fixed input channel that is slightly transformed by the style vector. So as a change to the previous StyleGAN versions, the input of the network isn't just a trained vector, but it has become a more complex layer. So what we are doing in this layer is first, while in initialization, we randomly sample frequencies and phases, which will be constant over the training. These frequencies and phases are then used in the forward function of the input layer, the new input layer, which first contains of an affine layer. This affine layer is just fully connected and reads or tries to estimate the transformation introduced in the style vector, what was shown in the visualizer. So the style vector itself contains information about the rotation and translation of the generated image, and this affine layer will try to estimate these rotation and translation informations. As an input, the style vector, which has the dimensions 512, in this case with batch size 4. We get this as an input to the affine layer, which then outputs 4 values. So T has the batch size times 4 values, which are the cosine of the rotation, the sine of the rotation, and then the translation in X and Y direction. And these are then used to apply the transformations inverse to the input informations, which are these Fourier features. So we use the phases, the constantly but randomly sampled phases and frequencies, to transform them and then calculate the Fourier features from them. Fourier features are linked to the Fourier transformation of an image, but then the sign of it is calculated. So we basically have a grid of informations about the output layer, apply the frequencies to them, then add a phase to them and apply the sign. So this is basically what Fourier features are. And then these Fourier features are weighted by a trainable weight as an output. So we have 1024 channels. So now we have this X, which has 36 times 124, which is basically already the output dimension. Then we add weight to each channel. So each of these 1024, and then basically just reshuffle them so that it matches the output dimension.
In the graphical user interface visualizer, we have the input variables that we can visualize, and it has resolution 36 times 36, and we can see one channel at once.
So that's X. So X is the output. And this also explains why changing the style vector transforms and rotates, because we have we learned the transformations, rotations from the style vector.
But what happens when we apply rotation and translation from the user input?
Yeah, that happens afterwards. So on top of the learned transformations, we add the transformations from the output. So this is in a normal run, this is just an identity matrix. But if we change, if we do this in the visualizer, we change this transforms variable, which is just part of the layer, and then applies them on top of the normal transformations. So what we do on the faces is we apply just the translation part of the transformation, so just translations, which is seen here. And on the frequencies, we apply the rotation part, so the first square. So we basically shift the faces by the translated frequencies. So we add the translated frequencies onto the faces, which themselves get added again to the frequencies in the grid. So the grid is just those values between probably minus pi and plus pi. So what we have 1024 channels of waves, which have direction and different squeeze pattern. And yeah, that's what we have. And then it's easy to rotate these waves, right? Or translate these waves, because this is pattern. Yes.
It's not a constant wave, or is it a constant wave? So
has different frequencies in each part, because the frequencies are multiplied to this grid.
So we have kind of basic structure, which is rotatable and translatable, because it has a repeatable pattern. Therefore, we don't have a loss of information on the edges, because it's just a repeated pattern. Very nice effect, because when you demonstrated this rotation translation, it was kind of extension of the image when you move it up or down. So in our case here, I suppose the input was 512-dimensional and the output is 4-dimensional for rotation and translation. So this A module is affine transform.
So the affine layer is just a fully connected layer. That's not the same as this one. And also the dimensions are different. As input, we have the style vector dimensions, and as an output, we have the number of channels as dimensions, just the number of channels. And this is then applied in the modulation. So we have the modulation. It's just multiplied, if I see it right. So we have the style vector multiplied by some weight exactly here. So here we have W512, and the output is styles, which has 1024, and styles is the S in here. So S is styles.
And this style we multiply again with a fully connected layer.
Yeah, with weights basically. Output of this step should be also the same, yes.
But what is then W?
No, it's the parameter, so it's trainable.
And then its modulation means?
So it's pixel-wise and channel-wise scale. So if we demodulate, we normalize the weight and then afterwards. But we still don't demodulate here. We demodulate, yeah, here. Here, that is just a step done before. So we normalize only if we demodulate, which is always on for this network. finally, I will discuss some additional changes in the StyleGAN3 iteration. All of these resolve around this, what is here called custom Cuda kernel. So compared to the StyleGAN2 architecture, where we had the modulation, demodulation, then convolution, and then this is passed to the next layer, adding some noise. So the first change is that the noise is removed, so we don't have this noise side channel anymore, but bias is still added, so the B that was added here is still added in this custom Cuda kernel. To get rid of the positional informations that come from the constant noise input from the side. All this is done in this function called filter reload or leaky reload. Additionally, we have this block that consists of the leaky reload which is wrapped in an upsampling and downsampling step, and finally a crop step. As mentioned, we first add the bias, so we have this first layer that gets the input from the input layer, which we discussed before. So X has a size of 36 with 1024 channels. So we then add a bias to the layer, go to the next step where we doing the upsampling filter called FU in this case, apply it to the input. The upsampling filter is described in multiple steps in the paper, which is first replaced. So in StyleGAN2, this was a bilinear filter, which was replaced here by a sync or jink filter with specific filter cutoffs and filter half width. In first experiments, they kept it constant, so they had a filter cutoff and critical sampled half width. But further iterations in the paper called G and T, they first removed the non-critical sampling. The filter width is not the half sampling width, but something below. And secondly, they made this filter cutoff non-constant, which is shown in this graph. So we have, instead of that being constant over all layers, it gradually increases over the layers, eventually reaching the maximum. So we have this filter cutoff that increases, except for the last layer, and therefore all the other filter parameters increase also. So this is passed all in this upsampling filter, which gets assembled in the synthesis layer initializations. So we initialize it as here we have this design low pass filter function, which samples the what's called here jink based filter from the Kaiser window and apply all the cutoff and width parameters, which gradually increase from layer to layer. So each layer has its own low pass filter. So this is then first applied as an upsampling filter, which also pads zeros in between the pixels of the input layer. So we now get, let's take some time, an upsampled image, so same number of channels, but each channel is upsampled to, in this case, 82. On this layer, the leaky reload is applied, so this is the next step. And finally, we downsample again. This is this one. So we get the size that we had before again. So this is one, or these are some major steps that were done on the paper. So first, experimenting with these upsampling, downsampling, and especially with the filters involved. So first before these were bilinear filters, but they were then first replaced by the sync filter, which resulted in translation invariance, and finally were replaced by the Jing filter, which also gave rotation invariance. Yeah, this is basically this block. What happens afterwards? So in the layer we are here, we applied the reload exactly, and then that's basically it. What happens in the forward function in each layer. So in this whole block, we just make some checks and then continue with the next layer. What also is applied afterwards, so the final configuration for translation invariance had this 3x3 convolution. In each block, this was replaced for the rotation invariant version with 1x1 convolutions. And to counteract, we had this increase from 512 to 1024 channels, as we have it here in the final version. As we can see in the layer section of the visualizer, the layer sizes don't simply double, and they don't do in a regular spaced manner. This is connected to the sampling size increase. So since they diverge from critical sampling, they dynamically increase the sampling size with each layer, which is shown here. So because the cutoff frequency linearly increases till the end, also the sampling rate increases in this step format. So as this is log frequency, each step means a duplication of the sampling rate. And if you compare, we see that for each time the sampling rate doubles, the output size of each layer increases. So, for example, from layer 1 to 2, the sampling size increases, and so the output size of layer 2 is also increasing. Note, the increase is not the double, but something different. So all this has to do with this custom kernel, where we have upsampling with low pass filter, then the leaky reload, and the downsampling also with the filter, and then some conditional cropping in the end. So what is done each time when the sampling size doubles, the first upsampling step is not just 2 times but 4 times, and the downsampling size stays at 2 times. So effectively the activation result is doubled in the end. Detailed shape progression or size evolution of this block. First for layer 1 and 0 and 1, which don't change in size for output. So we have 36 times 36 in the input. Then the real upsampling is done by inserting zeros in between pixels, which results in a doubling size. Then, as mentioned, the image is padded with zeros around, which they found that 10 pixels is enough. So we add 11 pixels at the top right, 10 pixels at the bottom left. So we get another increase in size. Then this filter, the low pass filter, because of border conditions, reduces the size slightly. So we get small decrease in size in this step. So this is all happening in this first upsampling step. Then the activation, the leaky reload is applied, which doesn't change the size at all. And then finally we have the 2 times downsampling, which means we first apply the downsampling filter again, which again decreases the size a little bit. And then we downsample this to half, such that the size becomes the same as before. This is for each layer where the sampling size didn't increase in the end. So like here for layer 0 and 1, and the same, for example, for layer 5 and 6. A little bit different for layers where the size changes with respect to the previous one. So we have for example, in here layer 2, we have 36 times 36 as input, but then upsample 4 times, so insert 2 zeros or 4 zeros 3 zeros in between, the size 4 times as high as before. Then we do a little crop around, so fit the size such that the sampling size in the end matches. Then we apply this low-pass filter, which again, as before, decreases the size a little bit. Then do the activation function as before, doesn't change the size. Then in the downsampling step, we first filter again, which decreases a little bit, and then downsampling by resulting in this 52 size. So here we can see why the sizes, even if the sampling rate doubles, the size won't exactly double, but do something different.
This discussion is a part of our survey paper, Deep Learning for Face Generation and Editing. To learn more, check the links in the description and visit our GitHub repository.